was writing them all but not. But since he was writing it, I might.
Okay. So this is the we have proved the theorem of optimal course space, but how do we actually make use of it? We need to compromise. We need to. I won't be able to get those eigenvectors in a computational feasible way. So I need to have what I call a quasi-optimal. First of all, we look at this Gauss-Seidel method, and there's one thing which is what I call a quasi-optimal one. First of all, I want to take a look at this R bar inverse. R bar inverse is this. So this operator is not so simple. If you do the Gauss-Seidel, the Gauss-Seidel is R is D plus L inverse. R bar is equal to R plus R prime R minus R prime A R. Now if you do the inverse, you have to invert that guy. By looking at that, it's not such a simple. I ask you this do 3 by 3, 4 by 4 things. you suppose to do the R bar inverse, and you haven't done it. But R bar inverse actually you can actually prove is equivalent to this diagonal thing. So if you take a sparse symmetric positive definite matrix, or maybe even semi-definite matrix, with positive diagonal, of course, then you can prove this is a linear algebra result. Eric, this is another problem you can think about in your exam. Okay.
You guys are worn out for the June exam.
It's ultimate. No, this is the Gauss-Seidel linear algebra. Give it a sparse matrix, okay? And for those who take sitting in here will get a better grade because you know how to do it.
You did the inside turn.
Yeah, that's the inside. So let's see. We have to be practical. So you take I like Gauss-Seidel, but we're talking about asymptotically. Gauss-Seidel, Jacobi, all these local methods all behave similarly. Okay. And this is actually a pure linear algebra in the sense that whether you have anisotropy or jumps, it doesn't really matter. This is a pure linear algebra result. This will only depend on the sparsity. Okay. So how many non-zeros on each row or something like that. And so this is something which you can prove in practice. It's not an assumption. It's a theorem. Well, it depends again on the sparsity. But so you when I say all right, this R bar A, maybe you do a D inverse A. Do you feel better? R bar A. Now I say the inverse A. The inverse A is just diagonal scaling. The eigenvalue is the same as if you really do diagonal scaling, you can do something like that. You can just scale the diagonal. So you can just look at that matrix. Okay? So that's the first thing. It's linear algebra. So then you want to say, this is what was solved actually I need these things I want to show this before. The best convergence rate is actually 1 minus the ANC plus 1 eigenvalues. You see this mu when you do the best approximation, the best thing you can hope. I told you before this I minus BA. This one will be greater equal to 1 minus mu nc plus 1. You cannot do better than this, okay? Because my optimal one is actually achieved on that one. Again, it's this minimax type of things. So if you actually get an estimate, that is kind of bounded by this guy, then you are in good shape. Or the when I say quasi-optimal, this is very important. I minus BA, this A norm is bounded by 1 minus, maybe a constant times mu nc plus 1. It's a multiple, but it still has to be less than, this quantity should be less than 1. Asymptotically, that would be the best you can hope. So, in order to do the linear algebra, because in the end, I'm going to only do multiple in a linear algebraic way, okay? So we have something I call M matrix relatives. This is just a special example. Because in most of the, if you look at the MG literature, in the early literature, even these days, they always emphasize these things called M matrix. And if you talk about the elliptic equation, take a Laplacian equation, this M matrix of the stiffness matrix has something to do with maximum principle. The M matrix, the inverse of M matrix is a non-negative matrix. Again, it's the linear algebra. If you have M matrix, well, what is M matrix? M matrix, you have the positive diagonal, the non-positive off diagonal, and what else? Have some kind of diagonal dominance. But anyway, the inverse will be non-negative. If you talk about M matrix, the inverse is non-negative. Non-negative matrix means that all the entries of the matrix are non-negative. This when I say this non-negative matrix is not symmetric positive, it's every entry of this matrix are non-negative. It's called non-negative matrices. Non-negative matrix has wonderful properties. But anyway, these are all the linear algebra things. But in practice, if you give us a stiffness matrix, I'm thinking of maybe at least I can solve Poisson equation, elliptic equation on a finite difference or finite element. I can solve it doing multiple on that one, algebraic multiple. But if you do this, like Eric said earlier, if you do quadratic element, there's no way you can get an M matrix out of it. But it's something called N matrix relative. When I say N matrix relative is the following. The diagonal is going to be bigger than the original diagonal, not smaller, bounded above. But the entire matrix norm will be bounded by the original norm, the A norm. This is what I call the N matrix relatives. So what is a, okay, when I say stiffness matrix and you have positive diagonal, right? Then you have off diagonal, maybe positive, maybe negative, okay? So the way I can do is that you can do a lemma is that if you do a, let's say, elliptic equation with a Neumann boundary, it doesn't really matter, you can do Dirichlet boundary condition. So you may have how do I get an MH relative? It's very simple. I take the off diagonal positive entries, put it in the diagonal. That's what I'm going to do. And if you do that, you can actually prove for the finite element matrix that will be a matrix. So if you put the off diagonal, the positive one into the diagonal is getting bigger, right? But it will not increase the. If you put those things, it's not going to increase the energy norm of these things. And you can you can actually prove it by some other way. So this is the if you do these things here, so the way you do it is that we do the NG. So you kind of manipulate the matrix and say, let's just make an M matrix out of it. I think this is one theorem we're going to do it. This is pretty much do the elliptic equation for second order elliptic equation for 2D and 3D with a rough coefficient, doesn't matter. So then you want to say that I want to make I choose the cost space. This is the linear algebra. You choose the cost space in such a way this diagonal kind of norm will be bounded by this NC of the eigen. You see, this is actually the point. Okay, you remember that the best eigenvalue, but the best cost space is that it contains all the first NC eigenvectors. Here, my quasi-optimal one means that I can approximate anything with some kind of error estimate so that it is bounded by the mu of NC, the NC plus 1 kind of eigenvalue inverse. If you do that, then I put all this together, I can prove that this rate of convergence will be quasi-optimal if this beta is not so big. If beta is big, this one will approach to 1. It's not good. If you have a relatively good bound, then you have a pretty good algebraic multigrid. That's the theorem, which is based on the. It's just the direct application of the theorem which I had earlier. So this actually is a pretty, in the existing literature, it's always a mystery why you want to do M matrix. How do you justify it? This is how mathematics is justified. This M matrix is the technique is an intermediate step to get your things, and you don't have to be M matrix. But anyway, so this is how this is a theorem like that. So the idea is that you design a algebra for its MU. So basically, when you design an algebraic multigrid for a given matrix, you only have to. It doesn't have to be an M matrix, but at least you can have what I call it doesn't have to. I really never say it is an M matrix. I call it any matrix with this property. I can. Then I can proceed. But you only have to design algebraic multigrid for this multiplied matrix. But then you use the prolongation restriction for the original matrix. So this actually guarantee, in that case, maybe in the rest of this lecture, I would say my matrix is actually already an M matrix. Because this AMG is very complicated in general, I want to at least give you some idea how this will work. At least one algorithm should work. Okay. So, okay, again, I come back to the theorem. This theorem is, I replace this matrix by this M matrix, and also I replace R bar by this D. So all this multiplication, all this replacement modification will not affect the asymptotic behavior of my algebraic multigrid. And so how do you choose the cost space? Okay, let me just so you want to listen carefully. This is a heuristic. It will depend on my theory, based on my theory. So algebraic low frequencies, but the things that we want to be able to, the one to capture is this. We want to capture. We want to capture this R bar A theta I, the mu I theta I. We want to compute this eigenvalue, but this one is kind of relative to, see this, if I say the A of theta I equal to mu I r bar unus theta I. If you think about these things, or you can say this is actually r bar unus looks like a D, right? The A of theta I equal to mu I, maybe, or D of theta I. But in any case, I still look at this r bar unus here. When I say it's something smaller, would be we talk about low frequency. Algebra low frequency is the small eigenvalues for this mu I. By the way, this eigenvalue r bar a is always less equal to 1, but you can prove. But so you want something to be, when you say the smaller eigenvalue, you will say it's less than epsilon. That will be called low frequency. Okay, here's the main idea of the cosinus. Okay, this is something, the key of all this algebraic, at least one of the algebraic multiplication methods. Please listen carefully about this one here, because I'm under, it's not proof, it's just heuristic. But it's based on the theorem. Let me read this. If a subset of vertices on which an algebraic low frequency, say, change very slowly, we want to choose, I want to reduce the degree of freedom. So if you take an algebraic low frequency, I want to be able to use the cost space to capture the algebraic low frequency. You got it? So I want to say, if I can find a subset, some set, okay. So that, sorry, this is important. If a subset on which an algebraic frequency on this point changes very slowly, like a constant. So then I can just say, I can just use one constant to represent all this patch of nodes. That makes sense? Is that what I call aggregation or whatever? Okay, if my low frequency changes very slowly on this patch of nodes, then I just say I'm going to use 1 degree of freedom to represent this unknowns. Then I do cosinus. We only need to keep 1 degree of freedom to represent in this. We actually call this vertices in this subset, we'll call it strongly connected to each other. When I say this is so I pick a node, I look at the neighbor. So I only pick the one that is, my low frequency, algebraic low frequency will be the eigenvector, low frequency of this one, which is kind of close to that one.
So is there a difference between, say, just keeping 1 degree of freedom or taking the average?
Oh, the same, similarly, yeah. You can take the average, but you need a cost space. Basically, this would be the prolongation or restriction you can think of to take. When you do the restriction, that's precisely the restriction. But you have a cost space, you have a fine space, you have a cost space. When the cost space pretty much say, okay, if this patch is I find that the element function is constant. Okay. Now, if the algorithm is subset, okay, one vertex deletes the rest of these things in this subset. So when you say that, okay, I'm going to do the cosinus. When you do the cosinus, that I pick one, then I remove the other ones. That's already represent the other one pretty well. Or you can say you can take an average, or you can keep one. Aggregate this subset together means that you still keep the things, but all the value on this subset are the same. That makes sense? Now the question is that what kind of indices of nodes that give you the low frequency that have almost constant values? This is something we need to figure out. Okay. So now, this is again the other heuristics here. So remember, this algebraic high frequency look like this, right? So we can rescale this thing so that if you look at the eigenvalue, so one of the interesting things that when you do the Neumann problem, if you think about when doing the Neumann problem, this is something which I want to tell you that when you have this matrix has row sum equal to 0, this is AUU, this one I can equal to that. This E is all the edges. Okay, so because again, this is linear algebra here. If you think about Neumann problems, which is make it easier to understand, basically you want to say row of Aij, say each row is equal to 0. The row sum equal to 0. If you regroup things here, you can say U transpose AU, that will be equal to sigma, all the Aij is not equal to 0, such that the negative Aij, Ui minus Uj square. So this one you can, this is pure linear algebra manipulation. Again, this one we will do algebra multigrid. So look at this thing here. This is something important, okay? You want this one to be small, all right? You want this one to be small, but you want to also find the patches that are very close to each other. Namely, you want to looking for this I and j so that ui is close to uj, all right? If the ui is close to uj, that means this one is going to be okay, so what kind of I and j pair so that this is very small? And but this quantity, each one of them, okay, first of all, I have a matrix right now, okay? Remember, all this negative Aij, all positive, okay? Because the edges I cannot be equal to j, all this are positive, okay? So I want this product to be small, and I also want this one to be as small as possible. So what would be the best idea to pick? If the Aij is larger, if this one is larger, that means this one is smaller, right? Huh? Because this product should be very small. So this means that you want to pick the Ij, the edge, this pair, so that this off diagonal is big. It's relatively big. We say Ij are strongly connected if this one is relatively large. So this means that I'm picking a point. I'm looking at my neighbors. Okay. I look at this TV game is called Weakest Link. What the strongest link? The strong connection. I picked the one that has the Aij as large as I picked. The other one I dropped it. I kept this one. Then I kept my neighbor that has the largest Aij. So that's would be my aggregation point. That makes sense? So you can actually say that how do you actually measure these things? For example, you can use Cauchy-Schwarz inequality to measure these things. You have to be relative size. For example, if there is S1 or well, there are different ways of doing things. And if you think about the theoretical estimate I was doing here, and if you also look at this theoretical estimate I do, suppose you do a cost space, you want to choose the cost space so that this is actually to make the smallest one. So anyway, but to make the long story short, if you want to usually have Aij is less than or equal to, Cauchy-Schwarz tells you that it's less than square root of Aii, square root of Ajj, right? This is the Cauchy-Schwarz inequality for symmetric positive definite matrix. So you look at the ratio. This is one way to look at it. You look at the ratio. If this ratio is bigger than certain threshold, it's always less than 1, then you call it a strong connective. But you have one sophisticated theorem based on one theorem. I know you can have a combination of these things here. For example, you have this quantity, which is based on my sharp estimate. I applied it to a two-dimensional case. So you can find some criteria to pick the strongly connected pairs. Those are the things you want to put them together. as a coarse space. If this one is large, they are strongly connected. So what is the? So wait a minute, we don't have. Let's see how much. Okay, here's the deal. So how does the AMG pre-process? So first of all, you pick a MHU relative. This applies to all the matrix problem for second-order elliptic equation. So you do MHU relative. So you form a filter, namely that you remove the weakly connected edges from AM. You drop all those things. So here's how I understand this business. I always kind of get a little bit confused. So how do you drop the edges? You make these things, you drop the weakly connected edges. So we imagine the cosine graph with two different steps. First step is to remove some edges, and the second step is to remove some vertices. The second step is the goal. Namely, you want to remove some vertices, right? I want to remove the vertices so that I have fewer degree of freedoms. So let us examine how the second step is carried out. We either aggregate some neighboring vertices together or pick some degree of freedoms.
What's the meaning of MIS?
This is maximum independent set, but anyway, this is a little bit, again, this is a graph. You guys study graph theory, right?
Sort of 6 classes.
Yeah, okay. One of the 6 classes. There's one in the right audience. So all these algebra models pretty much use our graph theory. You have maximum independent set to pick up. Then you look at the neighbors. And so you keep basically you just keep the strong connected vertices. Then you aggregate them together, or you get rid of all your neighbors, pick one to represent your coarse field functions. So that's pretty much my choice of coarse spaces. Okay? The classical AMG basically is that you find the maximum independent set of this fielded graph. Which means that you just find a good representative of the strongly connected set. For aggregation method, you just aggregate this graph using some local optimization algorithm or greedy algorithm. So then you form your cost basis, your cost basis, or propagation matrix. I don't know. I hope you get some rough idea. But if you want to know the detail, you got to read the paper. And I'm happy that we are able to. This was the idea of developing in the literature, and over the years, this was something survived. But they are indeed quite reasonable based on the theorem we developed. And this is actually the method used. The two types of method basically is what they call a classical AMG and aggregation. Aggregation basically you have some you group some sub nodes together, subset of nodes together. You put only 1 degree of freedom there. When you do the prolongation, you do an average, and when you do the classical AMG, basically you pick 1 degree, you drop the other nodes, you do some cosine. And classical AMG was designed for Lagrange type of element. When you have a nodal value, it's pretty much the degree of freedom for the nodal value. And these are the two major type of algebraic multiplier method. In this hyper, in Lawrence Livermore National Lab, they have this package. They're using classical AMG. I believe in Chernilo they have aggregation AMG method in there. Good. And they both work quite well in practice. And the heuristic which is based on the theory is on this. But the thing is that as a mathematician, then you say, okay, so what if I give you a whole complicated equations? So maybe is that here, or maybe not. This is not here yet. So the if you give me, for example, anisotropic problem, you have some, or you give me some jump coefficients. Sure enough, if I take the cost spaces by the strategy I'm explaining here, we can prove uniform convergence for multi-grid method, a two-level method. And actually, the algorithm works beautifully for general, for multi-level cases. But again, to prove the multi-level case to work uniformly is still an open problem. But practically works quite well. So based on this theorem, we believe we do have the right heuristics. And I think we can justify this algorithm in the two-level cases. Maybe I have to stop, I guess. Anyway, I will stay around to have discussion. Maybe I'll figure out what to. There are lots of things we can talk on. Wednesday I'll talk to Eric maybe what we